Welcome back. So, in today's video lecture, we will try to cover the application of the surfactants, right? And let's in today's lecture we will see how we can make use of the CMC, that is critical micellar concentration, the ability of surfactant to self-assemble to form micelles, right? And in so how this uh, the process can be used in dealing with some of the application, right? So one such application that we will see in today's lecture will be the micellar enhanced ultrafiltration. So we will take an example of treatment of wastewater containing the pharmaceutical and personal care residues, right, or contaminants, right? Let's begin. Yeah, so as we just described in today's video lecture, we are going to look at the pharmaceutical and personal care products. So removal of these products from the wastewater stream. So we are going to use the the ability to form micelles, right? The surfactants ability to form micelles. Okay, that is going to be the key point for us to look at in today's lecture. So let's start with let's say if you want to remove the pharmaceutical and personal care products from the water, so we will have to choose a right surfactant. Okay, so we know that whenever we add surfactant in the solution, so because there are it has got hydrophobic and hydrophilic part, the hydrophobic moieties or the hydrophobic parts would want to minimize its contact with the water, right? So they will self-assemble to form micelles in such a way that they will minimize its contact with water. So one such example is a spherical micelles. When they self-assemble to form spherical micelles, they will be arranged in this fashion, right? When they are arranged in this fashion, they leave the hydrophobic core or the oil core in which the organic matter, right, impurities, right, oil soluble impurities are trapped in this, right? So that is the going to be the advantage of this structure. Okay, so we'll start with the, let's say if we want to remove the pharmaceutical and personal care products, we will have to consider that we have the wastewater containing the target pollutants or the solute molecules. Then what we have to do, we have to add surfactant of desired surfactant. So depending on the which products that you want to remove, sometime you may choose depending on the ionic target contaminants, sometime non-ionic target contaminants. Let's say we choose a surfactant so that which will remove the pharmaceutical and personal care products via the two micelles, right? So when they form micelles, they will entrap these organic solute at the the core, hydrophobic core, right? So these are the solute molecules that we are talking about. So when you add sufficient quantity of surfactant, let's say above CMC, they will form these micelles, right? So that is the idea. Now after this, you will have some free monomer left, which are not, which are not participating in this entrapment process, and you will also have free organic, solutes, right? So the next step that we have to employ is the ultrafiltration unit. So this will contain pore size in a nano range, right? So that when you employ the when this micelles loaded the water stream, aqueous stream, passes through this ultrafiltration unit. The free monomer and the solid will uh, come out of this membrane as a permeate, whereas the micelles and the entrapped, right? Uh, you know, the solid molecules, right? The micelles, solid molecules entrapped within the micelles will be collected as retentate, right? So you got two stream in this. So in this way, you can actually collect or remove the free solute and the free monomer. But the important problem for us will be how to deal with this one, because you want to remove the solute molecules, but we also added another component in this problem, that is the surfactant molecules. So if we cannot remove the surfactant and solute from the micelles, the process will become costly affair, because you would not be able to reuse the surfactant molecules. So ideally, we need to recover the surfactant, and once again, it has to be reused. Only then the process will be economical. So for that, what one has to do is what we are going to look at as we move further, right? So next is going to be, we can explain, before we explain the technique to separate the surfactant from the the contaminants or target contaminants, we will first look at the various experimental parameters that affecting the performance of this membrane, right? This process. So there are several key parameters that we need to keep in mind. One is the membrane selection, surfactant selection, operating condition, and solutes, different types of solutes molecules that we are dealing with. So when we talk about membrane selection, the material of construction, the material of, using which membranes are made up, right? That is very important. For example, there are two parameters that one has to look at, very critically, is the molecular weight cutoff, right? So molecular weight cutoff is related to the pore size distribution and retention capability, and then the pore size. So what is the pore size of the membrane that we deal with? For example, the pore size should not be such that it is the larger than the size of the micelles, right, themselves. So what will happen is, if in such case micelles also will be passing through the membrane, so one has to choose the right pore size, right molecular weight cutoff. So general rule of thumb, general thumb rule is that the molecular weight cutoff should be at least 3 times smaller than the molecular weight of the solute that we are dealing with. Okay. Next comes the surfactant solution. Here, as you know, CMC plays very crucial role. So generally we should choose a surfactant for which the CMC is minimal, right? At minimal, so that you don't end up consuming too much surfactant, right? Say for example, if you choose a surfactant for which the CMC is on the higher side, which means that you have to use a lot of quantities, right, for the operation. So that will lead to a costlier affair, right? So one has to choose a right surfactant which has very low CMC, right? So that you don't so that the economically the process will be viable, right? The second point to cover is the aggregate structure and size. So what is the size of the micelles that we are dealing with? Size should be little larger than the pore size that we are dealing with. Okay, so one has to choose accordingly. And the next point that we should worry is are we going to use the single or mixed surfactant system? Sometimes using co-surfactant will be economical because the efficiency of the process may be better when we operate with the mixed surfactant system, right? So these are various guidelines when you want to choose the surfactant solution. Next comes the operating conditions. So what is the TMP, transmembrane pressure? It is going to be the driving force of the membrane. So one has to choose the TMP accordingly. pH. So sometime pH is going to be very crucial in addition to temperature and concentration, because when you want to remove the ionic impurities, so we might employ the ionic surfactant. So in this situation, when you lower the pH, probably we will generate a lot of protons around the micelles, which will help us keep the cations away from the micelles, naturally, so that it is easier for us to separate the cations from the micelles, right? So in such case, pH will be a very crucial parameter. Temperature, as you know, if you want to operate above or below the craft point or cloud point, controlling temperature will be very crucial aspect. Then the concentration, because one has to work around the CMC, critical micellar concentration, and you cannot, one should also vary of using the concentration, because if you use too much of concentration also, probably the solution becomes more viscous, so it will end up you might end up there will be more pumping cost, right? So that will become a costlier affair. So that's why one has to choose the right operating conditions for the process that we are talking about. Then comes the solutes. Here, whether you are going to remove the ions or organic molecules, okay, or sometime heavy metals in the form of salt, right, or the singular mixed solute system, whether you are going to target only one particular type of pollutant or multiple pollutants. So these are various questions that one should ask prior to any application, right? So we will look at other mechanism through which the membrane clogging will take place, right? So this is very important aspect. So before we look at the strategy that we will use to recover the surfactant, we will have to also understand in the mechanism through which the clogging of membrane takes place. Okay, so let's say if we deal with two kinds of the membrane, one could be hydrophilic membrane. Other type of membrane that we may often deal with is hydrophobic membrane. So in the case of hydrophilic membrane, so let's say the membrane is that we use sometime is functionalized membrane, okay, so that to make the surface hydrophilic. So surfactant, sometime some surfactant that we use often because it has got head group and tail group. The head group carries some charge on it, so there can be a hydrogen bonding between the head group and the surface of the membrane itself. So you can expect the monolayer of the surfactant formation on the membrane surface. As soon as the monolayer forms, because the tail is hydrophobic in nature, it can attract another layer, okay, of surfactant through hydrophobic interaction between the tail group, between two tail groups, right? In this way, you can expect a bilayer formation on the membrane, but there will be no further growth on this because the between head groups there will be electrostatic repulsion. So most likely there will be no growth further. So favorable the arrangement will be bilayer arrangement on the membrane surface. So in this way, you can expect that the surface of the membrane will be clogged, right? So it will hinder the process of transport. This is one mechanism. The other mechanism is it can also be sometime clusters. So micelles can also get attached to the surface through the hydrogen bonding. So in this way also you can expect the hindrance. The other way of hindrance is when you deal with the hydrophobic membrane surface, you will have the surface will share the hydrophobic interaction with the tail of with the tail groups of the surfactants. So in this way, you will expect the monolayer formation on the surface, but there will be no further layer on the above this monolayer, because the head groups will experience electrostatic repulsion. So there will be no attraction or between head group as well as head to tail group, because there will it will not share great affinity between the head group and then the tail group, or between the head groups, right? So you would expect a monolayer formation on the surface. And the other way could be semi-spherical cluster. As soon as the surfactants self-assemble to form micelles, before even the complete process of micelles take place, because these tail groups are hydrophobic in nature, they can get attracted to the membrane surface. So in this way also you can expect the hindrance to happen. So in various in this via these mechanisms, the membrane surface get clogged from time to time. So these are something that we should understand before we deal with the treatment process, right? So here we will look at the recovering the anionic surfactants from micellar enhanced ultrafiltration, right? So we talked about we were here actually. Okay, we'll start from here. There are three ways you can actually perform the recovery. Okay, so here in this example, we have taken the ionic surfactant and the ionic pollutants. Okay, this example is not given for the micellar enhanced, but the same strategy can be used or applied even for the case of the micellar enhanced separation. Now our starting point is going to be this one. So let's say we have got the ionic surfactant. So micelles are micelles are formed due to the self-assembly of the let's say anionic surfactant. We can take an example of SDS in this case. Okay, and around it you can see the cationic pollutants or cationic impurities. Okay, so it can be any cationic pollutants, right? So then you will see that, okay, so then when you perform the acidification, which means that when you lower the pH, right, of the solution, basically what will happen is it will generate a lot of protons, right? So when protons are generated around the micelles, naturally these cations will be detached from the micelle, because this proton will repel the cationic impurities, because they share electrostatic repulsion between the two, right? So if we employ the ultrafiltration again, you will be able to separate the micelles and the free monomer and the free cationic impurities. The disadvantage of this method is like high pumping cost here, and at the same time you will also have to end up with the free monomers, free surfactant molecules along with the cationic impurities. So this might again lead to some add to further operating cost, right? So the other method is based on the precipitation. Here, what we will do is we know SDS, the craft point of the SDS is going to be 13 degrees Celsius. Okay, whereas the craft point of the entire unit, which is SDS combined with the cationic impurities, is something, let's say 35 degrees Celsius. So these examples I'm just giving for you to understand better. Okay. So but again, these values are taken from the literature, right? So these data you can actually follow. You can follow this data so that you can understand this mechanism and a little bit more in detail, right? So let's say we have the we start from here. Now what we will do, we know the start point of the SDS, which is 13 degrees Celsius, and the craft point of this entire unit is 35 degrees Celsius. If I if I lower the temperature such that it falls below the solubility of the surfactant, now what will happen is surfactant will settle at the bottom naturally. They will precipitate out from the solution. What you will have is, in the true solution, you will have the free ions alone. So it is very easy to separate these free ions out from the mixture, right? The next, last but not least, is going to be the cloud point extraction method. In this case, what one has to do is, from here, you have to perform the acidification again, which means that you have to lower the pH so that protons will be generated right around the micelles, which will keep the cations away from the micelles, right? Then, by operating the temperature such that you are above the cloud point, so what will happen is, in this mechanism, what will happen is surfactant will phase separate from the true solution, and what we will have in the mixture, in the solution, will be just the free cationic ions, right? In this way, it is easy for us to separate surfactant from the cationic impurities, and this surfactant can be again fed, reutilized for the removal, for the application of treatment, wastewater treatment containing the pharmaceutical and healthcare products. Okay, the same strategy can also be used for the micellar enhanced process. Okay, so I think it would have given a good insight into the recovering of the anionic surfactants in this example. We will stop here. We will continue from the next lecture. Thank you.